Hey guys, today we're going to do Chapter 9, Section 1, which is starting our chapter on exponents, and Section 1 is on exponential growth. So for the last two sections we've been talking about exponent rules and how to simplify equations with exponents in them. Now we're going to start talking about functions that are exponential. So an exponential function is of the form ab to the x, where your a is non-zero, your b is greater than 0, and your b cannot equal 1. So I know that my b can't equal 1 because if I raise that to a power, 1 to any power is just going to be 1. So that would actually give you a constant function rather than an exponential. I also know that my a cannot equal 0 because if it does equal 0 and I multiply by 0 every time, that's just going to get me 0. Again, that would just make this a constant function. Okay. So b is called your growth factor, so that's that value here. It's your growth factor because it tells you how much the function is growing every time. Some examples of exponential functions that we've seen before are our geometric sequences. So remember, that is of the form your first term times your r value to the n minus 1. Notice that I'm raising that to a power of n, therefore it would be considered exponential. Also, your compound interest formula here would also be considered exponential because you're raising it to the nt. So anytime that you have a variable as an exponent, that's considered an exponential function. So something like y equals x squared, that's called a power function. That's different than an exponential function, because when you have a number as an exponent, that's considered a power function. When you have a variable for your exponent, that's considered exponential. So if f of x equals ab to the x, if you know the initial amount a and the growth factor b, you can write an equation for the exponential function. So this a value here, we call that our initial amount because that's whatever you start out with, and b is the growth factor because that's how much you're increasing by. So the Consumer Price Index, CPI, measures the cost of goods and services in the U.S. In 1980, the CPI was $100. Between 1980 and 1990, the CPI rose at an average rate of 4.7% per year. Let x equal the number of years after 1980, and let y equal the CPI. Then the formula y equals 100 times 1.047x can be used to estimate the CPI. Okay, so real quick, let's just talk about how they got that equation here. Remember that your a value is your initial value. So they're telling us that initially in 1980, we had $100, so that's going to be our a value. They're also telling us that we're growing by 4.7% each year. So if I'm growing by 4.7% each year, that's not just 0.047, that's going to be 1.047 because I have to grow. So that's where this number comes from. That's your growth value. And then I take it to the x. So if I want to graph this equation on my calculator, I'm just going to get out my graphing calculator. I'm going to type that into my y equals. So I've got 100 times 1.047 to the x. And when I graph that on my calculator, okay, for your window, they're telling us that x equals the number of years after 1980. So I'm going to just go from 0 to 10 for my x values. For my y values, that's the CPI, and I know that it starts at $100, so I'm just going to go from 100 to 500 and see if that works out. Okay. Looks to me like that one didn't work out very well, so I'm going to change my y values to be a little smaller. I'm just going to try 100 to 200. Okay, that one worked out a little bit better. So here's the graph that I got, and that is with a window from 0 to 10 for your x values and 100 to 200 for your y values. So then it says use the graph to find the CPI in 1985. Well, if I want to find the CPI in 1985, I'm looking for when x equals 5. So I can actually go to my table. So I'm going to hit second graph. I'm going to go to my table and I'm going to search for 5. And when I get to 5, I get a value of 125.82. So that means that in the year 1985, my value was $125.82. Okay. Then it says, estimate the year when the CPI will be approximately 250. Well, I can do that on my graph also. If I just keep scrolling down till I get 250, okay, I notice that my 20th term gives me 250.57. So, when x equals 20, that would be the year 2000. Okay, so we can use our graphs to estimate our exponential functions if you're not sure how to solve them. You can also just plug in values. The world population in 1985 was 4.9 billion people. At the growth rate of that time, the population would double every 35 years. Write an exponential equation modeling this situation. Let x equal the number of 35-year periods after 1985, and let p equal the population. Okay, so if I want to write an exponential function for this, remember that my functions are going to be in the form f of x equals ab to the x. So, a is my initial value. My initial value was 4.9 billion. So, that would be this big number here. Okay, 4,900,000,000. Okay. The population would double every 35 years. So they're telling me to leave x in terms of 35-year periods, so I would say that's doubling. Okay. And let p equal the population. So I'm going to change this f of x to p. So I know that represents my population. And it says, with this model, what would be an estimate for the world's population in the year 2000? Well, I know that my initial value was in 1985. So if I want to find for the year 2000, I know that that's 15 years. The problem is that my x value is in terms of 35-year periods. So I can't just plug in a 1, I can't plug in a 2, I can't plug in, just a whole number. I'm going to have to think about this in terms of fractions. So I know that every 35-year period I double, so I could say that this is 15 out of 35. So I'm going to plug in 15 out of 35 for my x value. When I plug that in, I get about 6.6 billion. Okay? So in the actual world population in the year 2000 was 6.05 billion. So we can see that that was actually a pretty good estimate. All right, then part C says, what was the population in 1980, assuming the same growth factor? Well, I know that my initial 4.9 billion was in the year 1985. So if I wanted to figure out the year 1980, that's 5 years before 1985. So that's the equivalent of me plugging in a negative 5 over 35. So I'm going to do that. So I've got 4,900,000,000 times 2 to the negative 5 over 35. And if I plug that in, I get approximately 4.44 billion. Okay, and that's everything for section 1.